Okay, so we have Davide Piras for, well, you'll tell us.
Yes. So I hope you can hear me. Let's see if this works. Okay, good morning, afternoon, evening, everyone. My name is Davide Piras. I'm a postdoc in Geneva, and today I'm going to be talking about an application of machine learning to theoretical physics. But before we jump into the talk, I need to apologize. And the very simple reason is I don't find my title very convincing, and I spent countless hours trying to understand what's the best way to come up with this. The original title was just a subtitle, this extending ΛCDM with representation learning. Oops. And then I remember reading this paper, which is a April Fool's Day paper, but it shows that if you have a colon or a semicolon in your paper title, your title becomes cheekier, and then you get more citations. So I said, yeah, let's add this less is enough at the top. And I don't know if this is going to make my title more cited, more cheeky, but that's a clear reference, in my opinion, to the less is more way of saying. And in my case, it's going to be less parameters or fewer parameters if you're a native speaker is enough. But also, as I'm an AI researcher, I of course ask what any AI researcher would do, and I asked ChatGPT to come up with a much nicer title, and I don't think it worked, so I'm not sure why this, okay. So the new title was this, Enriching ΛCDM. And you can see my very disappointed face there if you go to the slides. Yeah, it's going to be small, but you have to go online and see the slides. So yeah, I think we're still safe with our jobs and material for our debates in the next few days. But the best way for me to present my talk is to go through the title and break it down for you. And I'll start with this extended ΛCDM. And I'm sure you're all familiar with ΛCDM. To please the organizers, I'm not going to go through a full review. You can have your usual picture with cosmology and everything else. But for me, lambda is going to be the cosmological constant, which explains the accelerated expansion of the universe, and then CDM stands for cold dark matter. And we know that this very simple model is in agreement with many, many observations from Planck and many other surveys, but we know it's not the entire story. We know it has some problems, and for example, we know there are many tensions, which we also discussed a couple of years ago about H0, about S8. We don't know what dark matter is, we don't know what dark energy is, and there are many, many other problems. So this is why people in theoretical physics and mathematicians come up with beyond ΛCDM models, and these models have extra parameters. And I'll give you a few examples. So with CDM, if we start from a standard set of parameters with the energy density or variance and matter, Hubble parameter, and other couple, then we can think of other models which build on top of this, like WCDM, which adds W0 and WA. I'm not going to come back to this in a few slides. F of R, if you're a bit fancier, you assume the Ricci scalar is not a scalar in Einstein equations. And I'm sure you're all familiar with this, the Dvalika-Vodazzi-Porati model. Who doesn't know this? And this adds an extra parameter about explaining how geometry works in more than 5 dimensions. But in this sense, we can add even functions, and these functions have an infinite amount of parameters. And this is where Bayesian analysis becomes very problematic for the curse of dimensionality. And this is where we ask ourselves, can we find a common parameterization of all these models, and why not using machine learning? And this is where we jump into the second part of the talk, which is representation learning. By representation learning, I simply mean something as simple as that. We take an encoder-decoder structure. We take some data as input. We map it through the encoder. The encoder can be whatever you like. It can be PCA, it could be a CNN. This is mapped to a set of variables, a low-dimensional set of variables called latent space, and these are usually called latent variables. And these variables are used to make some predictions through the decoder. And what we care about here is this bottleneck, this set of latent variables here, because we want them to encapture and capture all the information that we care about in our data. And so we also want them to be independent. So in our case, as an example, we decided to look at power spectrum boost. So matter power spectrum have been mentioned a few times, and they will be mentioned many times in the rest of the week. We look at 4 different redshift bins. We look at different wave numbers, and this is our input data. And we actually take the ratio between the power spectrum in these extended models with respect to the power spectrum in ΛCDM models. And this is why we try to use the extra information which is captured by this new extended model in the input data. And the task here is just to do reconstruction. So this is a simple beta-VAE, a beta variational autoencoder, but I'm not going to go into the details of the architecture now. And also, on top of that, we also concatenate the CDM parameters to the latent space variables, because we want to encourage the model to find what's beyond ΛCDM. And this is work which we have done with Lucas and Breezer in Geneva, and we're also now working with people in Edinburgh. But as a first application, and also as an explanation of why I can already state less parameter is enough, or fewer parameters, we look at dark energy, at a very simple dark energy model, this WCDM I already mentioned. Very briefly, this has 2 extra parameters, W0 and WA, which modify the dark energy equational state to vary over time as a function of a scale factor A. And since we have 2 extra parameters, we would expect to have 2 latent variables to be sufficient to predict all the power spectrum and everything that we like. 2 latent variables should capture all the information in the data that we care about. But this was not the case. Actually, I mimified the situation. If you're not familiar with this, it's about Star Wars. But we were expecting, since we have 2 extra parameters, we only need 2 latents. But that's not going to be the case. And I'm going to show you some results in a very flashy way. So on the left-hand side, you have the results with 1 latent variable, and on the right-hand side with 2 latents. And even if you don't know what you're looking at here, you can see that these results are pretty similar between the 2. And if I tell you that as a function of wave number on the x-axis for 4 different redshift bins, what you're looking at here on the y-axis is how many sigmas away is the prediction from the decoder with respect to the ground truth, and saying that, of course, lower is better, so fewer sigmas. What I just want to say about this is that they are very similar. And in fact, we can conclude from this that with 2 variables, yes, we can maybe capture the entire information, but with 1 variable, we already have still very good results. If we add a 3rd variable, which I'm not showing here, the results are identical to the 2 latent case. And so for this, I can now conclude that 1 variable is enough for WCDM. But this is not the end, because we also want to analyze and investigate what's happening in the latent space, which will also be discussed further tomorrow during the debate. The first thing we look at is mutual information, and I'll very briefly mention what's mutual information. It's a measure of dependence between random variables, which goes beyond the linear Pearson correlation coefficient, very well established in information theory, as its own units, for example. But despite being very simple to define, it's very hard to estimate, especially in a robust way. And no estimator which is available in the market returns an uncertainty of mutual information. So this is why we came up with our solution, which is using Gaussian mixture model to perform a density estimation, and then using bootstrapping to get an uncertainty of mutual information. And we have this GMM-MI public code available, and we call this Jimmy. I don't have time to go to the details of Jimmy, but this is work done with Irene Paris, Andrew Ponson, Louisa Lucy-Smith, and Lilian Guo, who is also going to present her work on halo formation using mutual information. And how we use mutual information, we use it to calculate if the latent variables are independent, so are they disentangled? And we also measure the mutual information between the latent variable and the model parameters. Why? Because then we can have a look at tables like this. There's AD equals 1 is the latent variable, and we measure how strong is the dependence with respect to W0 and WA. So we can see there's a very high dependence. It's much more than 0. And if you also measure the mutual information between this latent variable and the other CDM parameters, we find little or no mutual information, meaning that our architecture was successfully able to extract the extra information and compress it down to a single variable. And then if you look at the second and third latent variable, we can see that in the AD2, BD2 case, the variables are dependent on W0 and WA, both of them, while the last line is the C latent variable doesn't carry any information whatsoever on W0 and WA. We also use symbolic regression. I don't have time to tell you now what's symbolic regression, but you can check out the review on Wednesday. There will be a much broader review. But the idea is that we want to have an explicit form equation linking the latent variable with the WCDM parameters. And drum roll, this is the equation that we get. This is the best equation linking, having the best compromise between accuracy and complexity. I don't find this very interpretable, but I'm sure there are many experts about symbolic regression in the audience that can tell me more about this. But in a provocative way, I would like to maybe say that this could be analogous to S8. S8 is a combination of sigma 8 and omega m, which is much better constrained by weak lensing rather than the 2 sigma 8 omega m parameters independently. And in a sense, we're doing the same exercise here, where we say that W0 and WA can be compressed down to this single latent variable that machine learning found. And maybe this could be the next parameter to target in upcoming surveys. And with this, I'll just go through the conclusion very briefly. So we only need 1 latent variable to predict WCDM multi-power spectrum, and we use this representation learning approach to find it. Then we use mutual information and symbolic regression to investigate and interpret the latent space. And now our goal, our plan is to use the same framework with multiple beyond-ΛCDM models and also different summaries. It could be CMBCLs, but also full field level maps to find this common parameterization across these different models. And before I stop, I also need to advertise our other work with Alessio Spuri-Mancini. There's a poster, I think the most amazing poster you've ever seen. There's also a nice video that you can check out. This is about accelerated Bayesian inference with Hamiltonian Monte Carlo and neural emulators. And with that, I'll stop here. Thank you.
Thanks a lot. Thanks, Davide. That was very interesting. Do we have a question here? We already have a question here.
Thanks for the talk. So the fact that it reduces to one variable, is that true just because you're looking only at matter power spectra? Because I imagine if you add in, distances measurements, that you might get a more complex parameter space.
I think so, yes. I think the results we find are very tightly coupled to the data we use. So just look at matter power spectra. So that's one parameter to describe only matter power spectra. If we add other data, which is actually I think we're doing now, then we hope to find something, maybe two parameters might be enough, maybe we find one, and we're just exploring. So it's highly dependent on the data that we use, yes.
Another question from Licia.
So the combination of omega matter and sigma 8 was found by seeing what the data actually constrain, right? Why is this similar in the same way? That is what the data would actually constrain. So can we see the same combination in the WWA banana plot?
I think this is something that I should do next. I don't know. I don't know the answer to this now. I think, in a sense, I don't think symbolic regression can find the best equation that maybe humans will come up with, but I think a combination of the two might give something that very interesting. So this is our upcoming work, yes.
Thorsten? You can store an arbitrary amount of information in a single real number because you have an infinite number of digits. So the question is more, how sensible is the order of, say, pictures or spectrum which you put on the real line with your single variable, right? You can make a piano curve through a very high-dimensional space, but no human will understand it. Nevertheless, it's there. So my question is your one-parameter representation sensible in certain things that one can interpret it, or is just a way to compress something complicated onto the real line?
It's a very good question. So the first thing is, if I had stopped my talk at this result, I would say, here, I would say, I don't know. But then we want to show that we can use something like mutual information, and now even maybe symbolic regression, to actually check and interpret this latent space. So I think it's very important not to stop here, otherwise your question is very valid, and I think there's no way for us to know if it's just this one variable with infinite digits, for example. Yeah. So yes, we need to do something more.
Mutual information will not tell you because it's invariant under reparametrization of your coordinate space, but symbolic regression assumes continuity in the interpretation space, so that might be informative.
And my, say, counter-argument to symbolic regression is I find it very highly dependent on the prior that you put, essentially, on the set of functions that you allow the genetic algorithm to fit. So I don't know how to combine these two, maybe this mutual information with symbolic regression, or just some better way of symbolic regression. I think there will be many talks after mine about symbolic regression. So yes.
Thank you. We have questions in Slack. Do we? Matt? Slack? Yeah, take the mic.
Just one. Is there an explanation for why the redshift 0.48 sigma is higher for 2 than 1 latent variable?
It's a very good question. So it could be, very naively thinking, is that the network has found an effective value of W. So if you look at this.
Can we get the slides?
So if you can see the slides, this is the equation for. This is the equation for the dark energy equation state. So maybe there's an effective value of W of A, which the network has found. But there's no easy way for us to test this. But I think this is what it's one way to interpret the results without looking at mutual information and symbolic regression. So yeah, I think it's a good sign. It's a sign of this thing, of an effective value of W of A.
Okay. New York, any questions on your side?
Yeah, go ahead. You can use the mic on your chair. Can you hear me?
Sure.
Hi.
Hi, yes, this is George Valogianis. Great talk, very interesting. So you talked about the future work and how you think about applying this to future more complicated models. So I'm curious to see how this projection to only one latent space variable is going to scale up when you work with something more complicated. Like, because f of r, for example, as you mentioned, you have a scale-dependent modification, you have screening. So I was wondering if you have any insights or expectations about how this would work there.
So I don't. The models are training now. The good thing is that now we have all the data. We're using this React framework developed by Benjamin Bose in Edinburgh. And then we can have this DGP model, f of r, dust scattering, WCDM, and neutrinos as well. I don't have any results yet. I think it will be much more than one latent. Maybe two, maybe three, but not just one. That's my take, my expectation. I'll tell you next year if they invite me again to give a talk.
Thank you. Looking forward to that.
Okay.
Any other questions?
Other question in New York?
Yes, so this is Paco. So when you train the compression initially, do you vary W8 and W0 in a very large range, or this is kind of more effective? Because I was wondering, for the symbolic regression, maybe I can, this, at the end of the day, this is like a, it's a simple linear relation. So you can probably describe this, I don't know if I explained this well.
So the question is, how broad is the range of W0, WA, if I understood that correctly? And that's
yes, exactly.
So the values are the one essentially that allow for numerical stability, so it's as broad as possible. And the only limitation is about omega A, because we cannot go above 0.2 currently for some numerical instabilities. But we double-check the results between CAMB and this React framework, and we get the same results. So we think it's essentially, it's quite broad. Yes, it's broad enough.
Okay, so I think we should stop here for the next talk. Let's thank David again.